Good afternoon, agents and codebreakers. Welcome back to the Northern Ireland Raspberry Jam Live. This month, we'll be running with a cryptography theme, so you have the whole afternoon hacking and code breaking ahead of you. I hope you've been enjoying the Bitbot stream. That stream will be running all day, and it's there just to give you another chance to draw and mess around with the Bitbot, as we had some technical issues last month. We'd like to thank Nitech Solutions Limited once again for offering their lovely office space and their really cool workshops for letting us host the Raspberry Jam here. And today's schedule will be available at workshops.niraspberryjam.com/public_schedule. We have two great cryptography workshops. We have the super secret Signal Sender workshop with Alan and Abby, and the Python ciphers with Kevin and Charlie. The worksheets for these will both be available in the YouTube live stream chat, and if you booked an Eventbrite ticket, you'll have had an email sent to you earlier this morning with all the links to the worksheets. As a break between the workshops, Agent Techno Teacher will be taking you on a tour of a super secret location to see the world's very first digital computer. And to finish up today, Charlie will be interviewing William, who is a regular Jam volunteer and now the National Ciphers Challenge champion, who won the Ada Lovelace prize of £1,000. To get started though, we'll be learning a little bit about secret messages with Alan O'Donoghue, a computer science educator, self-certified computational tinkerer, and most importantly, the founder of the very first Raspberry Jam, the Preston Raspberry Jam. This workshop is called the Super Secret Signal Sender, and we'll be encouraging you to answer all of Alan's questions in the live chat. You'll be using a little bit of microbit mate code, and that is a block-based simple drag and drop coding environment that we've used a lot in the Jam. But Alan and Abby will explain all of that for you.
Hello, good afternoon, and welcome. It's me, Alan. Say hello, Abby.
Hello.
Hello. So we're going to do some pair programming this afternoon, and that's great for me because I get to give the instructions and Abby gets to do all of the hard work. Are you okay with that, Abby?
Absolutely fine.
Super. Oh, super. We're going to build a super secret signal sender this afternoon. I was going to say it's easy to say, but actually it's not easy to say. Can you say that, Abby?
Bit of a tongue twister. Super secret signal sender.
That's pretty good. So what is a super secret signal sender? Well, people use them often. So sometimes people talk about codes and ciphers, and they sometimes get the two confused. Well, we're going to start off building something that can send secret codes, which is a signal of some sort. And then we may look at cryptography and ciphers. So, Abby, you can hear me. I know you can.
Yep.
If I said to you, Abby, 10-4, what does that mean?
Say that again.
If I said 10-4, Abby, what does it mean?
I'm not too sure.
Oh, did I not tell you? Oh, sorry, that was a secret code, Abby. Oh, the thing is, if I tell you now, everybody listening is going to, okay. So there are things that are called secret codes, and sometimes people listen out for these secret codes. So there's one you may have heard of called Inspector Sans. Abby, have you heard Inspector Sans?
No, never.
You've never heard Inspector Sans, right? Well, I think we should go and listen. So in that document you have on your screen, I've put a link in there to Inspector Sans, the wiki page. So if you just click on that for a moment, that should open up a wiki article. And it tells you what Inspector Sans is, but I don't know. Can you play the audio and see if it comes through? And if it doesn't, I'll just tell you what it sounds like. So I can't hear anything, but if you can hear it, it kind of goes like this. Boop, boop, boop. Inspector Sans, please contact the information desk. Inspector Sans, please contact the information desk. Abby, is that true that you've never heard that message before?
Never.
I think maybe you heard it, but you just ignored it. Because does it kind of sound like it's really... Does it sound like it's for you, Abby?
No, I would. You're probably right. I probably would ignore it.
Is your surname Sans?
I might pay
No.
attention to it a bit more.
And you're not an inspector, so you'd probably ignore it. So the point about this signal is it's actually to alert people. So it's usually used at train stations, maybe airports. It might be used on the London Underground. And I've been in lots of different train stations where I've heard it. But the very first time I heard it, I was a little bit curious. And I took out my pocket computer and I typed in, what does Inspector Sans mean? And it said, oh, this is a secret code often used to tell people that there may be some kind of security alert, something that they should be aware of. And I thought, well, it's not very secret if you can find out what it means on the internet. Does that sound a bit rubbish, Abby?
Yeah, just a little bit.
Or maybe most people who don't know what it is, they would just ignore it because they just think, oh, it's just somebody got lost called Inspector Sans. So there's a little bit of information that you didn't already know, but I think what they're trying to do with this particular message is they don't want, whereas if it said something like, hey, everybody, just need to look around. There's like a security situation. We don't want you to panic. What do you think might happen, Abby, if they said we don't want you to panic? There's a security situation.
I think a lot of people would panic.
Okay, so that's why we have the secret code. Now, Abby, so you're probably not been to lots of train stations at the moment. Could you think of somewhere where it would be useful for you to be able to send a secret message to your friends or some family members?
I'm probably in school. I want to send some secret messages.
Okay. Now, you and I haven't been to the same school, but are there ever times in the classroom you'd want to send a message to your friend and you wouldn't want other people to know?
Definitely.
Okay. Can you give me an example of one, maybe?
Maybe just to help me out in class.
Oh, yeah. You know, like when the teacher goes, Abby, can you tell me what is pi to 4 decimal places? And you're thinking, oh, I wasn't even paying attention. Wouldn't it be cool if you could send a secret message to your friend across the classroom and your friend would just shout the answer out or something else? And the teacher would say, like, let's say your friend's called Colette. Colette, why are you shouting the answer out? And it's helped you out. Wouldn't that be kind of useful?
Very useful.
Yeah. Can you think of any other situations maybe where you'd be useful to send a message in class to your friends?
I don't know. Maybe if I wanted a distraction.
Oh, because sometimes things happen in class and you don't want all the attention on you. So let's say you got embarrassed about something and your friend Colette knows that if she gets this message, she has to cause a distraction, like drop her books on the floor or cough really loudly. So suddenly everybody looks over there. Okay, I think we need to go and build something now like that we could maybe take into a classroom situation and test out. Abby, do you use a microbit ever? Have you got one? Do you know what one looks like?
Yeah, I know what they look like. I've used them a couple times.
So, but I'm guessing you don't have one with you right now.
Not right now.
Well, don't worry, because there's a virtual online microbit that we can use. So if you were to use a search engine or a browser and you went to a certain URL like microbit.org, so we could try that. I can't even remember. Oh, is that microbit.org?
That is makecode.microbit.org.
So I think if you went to the microbit.org website, you can then find your way to there. See, try that, microbit.org. I might have told you the wrong one. We'll find out. We're there. Now, does it tell you somewhere like, here's how you can make something with code? Let's code.
That
looks like it's a good place, I think. Yeah. So let's get started. See, you're used to doing it a different way, aren't you? What's that over in the top left? Make code editor. See there?
Yep.
Okay. Yep. So try there. Okay. Now, we're going to start a new project, okay? And the point of this project is we're going to send secret messages to other people in class. Now, what do you think we should call it? I mean, super secret signal sender is quite complicated. Should we come up with an easier name for it?
I don't know, maybe the 4 S's, because super secret signal sender.
Yeah, let's do that.
And
you and I will know what SSSS stands for, but it's like a secret shared between us. Yeah. Oh, 4S. Oh, that's clever. I thought you were just going to go SSSS. Okay. Do you need that? I would take that apostrophe out there. I have one in my surname and it causes me lots of problems. So I would just, 4S is fine. So let's create it. Now, I don't know if do you ever watch any films that might have like nuclear submarines or army soldiers or anything like that? Have you ever watched a film like that, Abby?
A few.
Or Star Trek? Have you ever watched Star Trek?
A little bit of it.
So they have what they call this like condition green or neutral status or low status low, where basically Abby's in class and everything's fine. She doesn't need any help from her friends and she doesn't need to cause any distractions. So we're going to create some kind of visual pattern that we can just display, something nice and pretty. So how would you start? What block would you use to start, do you think? I'm looking for... Can you see a block on the screen? Should we try that one? On start? Yeah. Okay, so we could start with that. And we need to put something in there visually. So is there like LEDs? I can see something there. See what it says LED?
Yeah.
Ooh, that looks a bit complicated. Is there one that's like something to do with display? What's in the more? See the more menu? Can we go in there? I'm looking for like an animation or a pattern or something. Is it in the basic menu? Is that where it is? Are we? There, show LED. So take that across and then just create some really simple pattern. It could just be 2 eyes and a smile. Okay, so will that do for now?
Yep.
Okay, now I think it needs to be some kind of pattern that changes so that people, like, if you can see, I don't know if you can see my hand, something that's like animated. So we could create another pattern like that one. You could either duplicate it or copy it and make another. Okay, and then just stick that below and then just make the pattern, maybe have it like a less smiley face or something. Just change the mouth. I wouldn't change the eyes, really. That's it. Now, can we look over on the left-hand side of your screen? Is it animating? Do we need to start something? Is there a button that we need to click to make it start?
And we restart this? Yeah, there we go. It moved.
No. Oh, it only did it once. Is there a way that we can make it to keep looping and keep doing it over and over again? Loops.
Maybe in the loop section. Repeat?
Is there one that... Because that says like do it a certain number of times. Is there one that just keeps making it do it over? Well, do that while through. Let's try that one. And I think we need to try and stick that around the outside. Yep. So move those. Abby, you've done this before, haven't you? Yeah. Now let's look at our simulator on the left-hand side.
It's going from one to the other.
Now, we can always come back later on and we can change the pattern of these LEDs to make it more interesting or more artistic. But we've basically got this is like our green status. Everything's fine. Now we need to think of what might we do. So let's say we've got a microbit on our desk attached to our pencil case or on your wrist or something like that. I think it'd be a bit conspicuous if you had it stuck on your head, maybe.
Just a little bit.
It would be a little bit. Now we need to find a way of having a pattern that would be different when we want our friend to see it. And that would be the secret code. So Could we, it says show LEDs, could you just over on the right-hand side of the screen, just start making a different pattern? And we'll call this will be our help pattern. So
Just
I would
here?
I would leave those two there. I would go back to the basic LED, go basic, show LEDs, pull that over, just like to the middle. That's it. And let's create our help kind of message. So what would it be? What about like the word help? Do you think that would be a good idea, Abby?
I don't think it would be very secret.
You're right. I was trying to catch you out. Did you see? I nearly caught you out. Did I nearly catch you out?
You made me think.
Yeah, okay. So it needs to be like almost the opposite, something that's going to confuse, or sometimes secret agents use the word obfuscation. Do you know what that means? To obfuscate something?
Not really. You're gonna have
It
to
means to
tell
hide
me.
something in plain sight. So something that most people won't think about, like Inspector sounds, contact the desk. Most people would just ignore that kind of thing. So could we think of something that most people would ignore, but it has to be different from the smiley face? So what would you do? It could just be a random pattern for now, because we can, or a shape of like a triangle or a circle or a square.
Or like a tree or a heart.
A tree. Let's do a tree. And you mean like a natural object with a trunk? You don't mean the number that comes after 2? Because I used to say tree when I lived in Ireland, and people said that's not a tree. A tree grows, and birds have nested. Oh, that tree looks a bit like a Minecraft sword. Does it need the base on the bottom, do you think?
Oh, probably not.
It looks a bit like a lollipop as well, or a Lego tree. It looks like a Lego tree. So the tree is help. Okay. Now, where do you think we're going to put this in? Where are we going to put this into our program?
Well, it can't be here because it's a secret code. I can only use it whenever I need to tell.
When something happens, like when you need help. Do you know, I've just realized I think we made a mistake as well. But we can always fix that mistake afterwards. In fact, if I don't mention the mistake again, maybe nobody else will notice. We've made a mistake. We'll carry on. So is there something, look at that menu, where it says basic, input, music. Is there something in there somewhere that's going to allow us when something happens? When something happens.
Or maybe whenever a button is pressed.
That would work great. So move that pink block. So we call these often conditionals. So if a certain thing happens, so we could test it now. So should we go over to the simulation? Press button A. So you have to click on the simulator. Did it? Hey, it worked. Did you see?
Yeah.
It was very fast. Just try it again. Yeah. It might just be enough for Colette to see. What if it kind of flashed a tree? Do you think you could do that? Or maybe that's something we come back to later on.
Maybe if I look through the menu to see what there was, see if I could flash it. Or
is there something in there that says flash? I think a bit like our animated face. I think we might have to find a way. That's something we could come back to a little bit later on. Now, what about the other message that we talked about, the distraction? Could we do another one for distraction?
There's a button B here, so we could do the same thing.
Okay, let's do that.
But with button B.
Do you know what, Abby? Just stop there for a moment. Just stop. I've thought of a way if we can save some time. If you go to the on button A show LED tree, I think you can right-click duplicate. Yeah, duplicate that. And just change where it says button B to A, to B, to and just change the pattern. And then, where it says on button A, if you just drag that back over to the other side of the screen, it should disappear. That's it. See, didn't that save a lot of time?
Yeah, definitely.
What are we going to do with all this extra time now? Now, we don't want the tree's not a distraction. We need something else. Oh, I've got birds on my shirt. What about like a shape of a flying bird? Because a bird could be a distraction. Like, whoa, look at the bird out the window, everybody. And that could be like the message that your friend would shout out, but it would still have to be like a secret. So it can't look too much like a bird. Yeah.
I'm not great at doing birds.
That'll do, because all we have to say is, Colette, if I do the bird thing, the code is you need to go, oh, look, it's snowing at the wind, whatever, and it's just a distraction so people are not looking at you. Because sometimes teachers can say, like, Abby, tell me the answer to, and suddenly you get all like embarrassed. Everybody's looking at Abby, and Abby feels like everybody's looking at her, and you press the B, that like the panic button, quick, cause a distraction. And your friend goes, oh, look, it's snowing! And everybody looks out the window, and it's not really snowing. And it could even be there's no windows in the classroom. So I don't know, but that's for your friends to worry about. Okay. So, what if you accidentally press those buttons in the classroom? That could be a bit annoying.
Oh,
Yeah. Could we do something so it's not so easy to press it? So it could be two things. Oh, like if you press button A and something else at the same time. I wonder if we could do that.
well, is there any more options here? Is there
What can you find? What can you see?
or
Oh, that said A and B. So it could be
Yeah.
if you press the two buttons together. So that's solved that one. That was an easy solution. Try it. I wonder how you do that on your computer, because you've only got one mouse.
Yeah.
So that's
Oh,
be
look.
hard to. Oh, that's
another button
handy.
has just appeared?
That just appeared. It's like a super secret button that we found. Yeah. So you could press that and test it. Yay. So that we know that works. Now, what about the other one for when we want a distraction? So I don't know we can use A and B this time. We need something else.
Trying to think here.
So it says on shake. So it could be that if you shake it and press the button, I wonder, is there a way of joining them together? How would you do that?
Well, I can't put it in there.
No, because it's already got that one. So, oh, I think I've got it. I think bring the shake back again for a moment. Oh no. Let's have a look where it says logic. See, there's a logic thing. See in the logic menu, because sometimes scroll down. So see where is there something like that says and? Okay. Right. Could we bring that over? So it's like if something and something, can you take shake over and put that into, I probably should have tried this. See the word shake? We need to find a way. Oh, I know. Go to the input menu. Input. There's this, scroll down. Is there something that says like shake?
If shake?
Oh, that's it. Put it in. And then if shake and button, go back to the input menu, scroll down, button pressed, and we change it to B. So it could be if you press the button and you shake it. Do you know what as well might happen? I think as soon as you start shaking it and your friend sees you've pressed the button, your friend Colette is probably going to know already we need a distraction. And when she sees the pattern, now it's hard to do this in the simulator, but I bet there's a thing called POV. Have you ever heard of POV, Abby?
I don't think so.
I'm going to show you something. I need to find like a pencil. There's a thing called POV. They call it persistence of vision, where you can do like magic tricks, where it's almost like if you do something fast enough, you can say, "Hey, look at my pencil, Abby. What do you think my pencil's made out of?" You see on the camera. It kind of looks a bit floppy, but it's not. It's just like a normal pencil. So the POV is persistence of vision. So it could be that as you're shaking it later on, something for later on, you could do a pattern, and then it could be like COLETT. That's not secret, is it? Yeah. Right, Abby. Do you think we've got a bit carried away? Do you think this is too simple?
Yeah.
It is too simple,
more
but
complex.
Well, we could find out ways of testing it, but I think starting it simple. You must have heard sometimes people say KISS, keep it short and simple. Have you ever heard that?
Yeah.
So how has it helped us by keeping it simple?
Other people can understand how to do it and how to replicate it.
Do you know what as well? I'm looking at the clock and it's just after 3:25, and we started at 3:05. So that means within 20 minutes, we quickly built something that's kind of not like real, but what's that word? There's a word that sometimes people use. What is the word, Abby? Prototype. prototype, that's the word I was looking for. So we've made a prototype, like an early model, to show people how it might work, and we can now develop it to make it a little bit more sophisticated. So any ideas about how could we make it better? We haven't tested it out yet, so it would be useful to test this at home. And did you say you actually do own a microbit? You just don't have it with you today?
Yes, I do have a microbit at home, but I just don't have it with me today.
So
But I'll be
yeah,
sure
I
to do
thought you'd
this when I get
said
home.
you have one at home, but you just don't have it with you today. So what you could do later on is you could test it to see. And I'm wondering as well, like if there was a way of testing it. So because obviously you don't want to wait to find out in this classroom.
Yeah.
Something happens, you need help, and it doesn't work. So how would you test it out?
I don't know.
Well, I wonder. See, I don't know if there's any way we can listen to people who are watching this, but if we could hear somebody now, what do you think they would be suggesting as ways we could test this out or try it?
To get a microbit or to use the simulator? Or...
Yes. Well, I would say obviously if you have a microbit, then
Yeah.
it's probably going to be the best way of testing it, because
Yeah.
it would look a bit awkward if just in class you needed some help and suddenly you took out your laptop, go and load up your code, and then show it to your friend and go, "Hey, Colette, look, the secret message on this," because it's taken too long. It's not really practical, and everybody's going to think, "What's going on here?" It's too distracting. Yeah.
Yeah.
I did have another question. Did you spot the mistake that hopefully people didn't spot? You know, when I was trying to get it to loop, to keep doing the same
Yeah.
thing over and over again forever without stopping.
I think I see.
Should we give that a go and see? Because we used while true. We could have probably just put it into forever and see. And there's little like arrows that says refresh. So I think if we click refresh, does that do the same thing? No, it doesn't seem to. So why is it not forever doing? Okay, now I am confused. Are we doing something wrong, do you think?
Yeah, I don't know. Is it still on the on start or something? And maybe if I got rid of that, or...
You see there's like a stop button over on the left-hand side.
Yeah.
Maybe press the stop. Take out the while true, because that might just move. I think we just detach it. No. Just move it to the side for a moment so we separate the blocks. On start and while true, just pull them apart. That's it. Where have they gone? Just
there you go.
down. Oh, it's doing it now. So it was like we created a block that wasn't quite finished and it was causing a problem. So we could have used forever. So did what we did earlier. Was that wrong, do you think? The first one?
It still worked. It was just...
You're right, it did work.
Not as easy.
It probably had more blocks than it needed.
Yeah.
Okay. So we have our forever pattern. We know if we press the two buttons together, it's that secret code. We know if we... Where's the shake one? Has that disappeared?
It's here.
We have to find a way of joining those together. On button B pressed. I think we need to go back and look at... Is it in the More menu, first of all? Might it be in the More menu that when a certain thing happens... no, it's not in there.
So.
Is it in the Input menu? So we're looking for...
anything.
We're looking for some kind of loop. Is it in a... Oh... Do you know what? I think we should have gone to the basic menu first. Let's go and look in the basic menu in there. Let's scroll down.
I don't think it's in there either.
You don't think so? I thought I just saw it then at the bottom. Okay, so we're looking for... We could put it in on start. We have on start.
Oh, yeah.
Yeah. And then we're checking to see if a certain thing happens. So we need to find... Oh, this is a challenge. So is it in logic? Let's have a look in logic here. If Ah, that's it. Look. Up to the top. If something's true, put that into on start. Drag that in there. Now we've got this this very long hexagonal block. Can we fit that block into where it says true? Oh, yes, we can. Now, can we take the blue show LEDs, which was the bird that doesn't look like a bird, stick that into there, into the green one?
Yeah.
Now, I think we're getting somewhere. Now we've got a lot of stuff on the stray bits of code. Now we can test it. So now there is a way of shaking your micro:bit. I think you have to move your mouse over it. But how do we press the button and do that the same? Try. Is it possible? Oh gosh, this is hard to test on the simulator. So we're shaking it. Oh, can you see the little shake thing up the top?
Yeah.
See where it says shake? Click there. Click B and then click shake. Oh, this is hard to test on the simulator, isn't it? So maybe for testing purposes, we might have to come up with another sort of condition. Well, okay, right. So we've been running 30 minutes in our workshop, so we've got a few more minutes left. Now, do you remember when we started? There was a document. It was a Google Doc I'd shared. It was the second tab in your browser. Let's go back to that. So there we are. The super secret signal sender. We talked about Inspector Sands and what we thought worked well and what didn't. And then I asked you, another one, rock, paper, scissors. Abby, do you ever play rock, paper, scissors?
I love rock, paper, scissors.
You do. Let's play a quick game now. So we go. We're going to go. Should we do a practice first of all? So I go rock, paper, scissors. And when do you display your token, your choice?
I do it on the shoot. I go rock, paper, scissors, shoot.
You do. Oh, you go rock, paper, shoot.
Rock, paper, scissors, shoot.
So it's like you go 1, 2, 3, 4, and then you display the paper or the rock or the scissors. Yeah. Okay. So shall we play one game now, and we'll see how we do. So we go rock, paper, scissors, shoot. So I've got a rock.
I've got some scissors.
You got scissors. So I won in that situation. Okay. Yep. Now, if I play again, if I tell you this time I'm going to do the rock again, should we do that?
Yep.
Okay, so I'll do the rock again. So rock, paper, scissors, shoot. What did you play?
Well, I went for paper.
No, that's not fair. Because that means you've won this time.
But you told me what you were going to do, and I wanted to
I know, but I didn't think you were going to use it against me. That's not really fair. Right, we'll play one more time. So far, it's one game to Abby, one game to Alan. This time, I'll do the rock again, okay? So rock, paper, scissors, shoot. What did you play?
Well, I went for paper again.
You did that last time. And you won last time.
Yeah.
You're not playing very fair, are you? Why did you... That means you've won 2 games. Oh, some friend you are. I think I should have had my panic button or my help button that I could have sent my message. So what was going on? How could I be better at my game then? How can I beat you at rock, paper, scissors?
Maybe if you told me in a secret way that I didn't understand what you were going to do.
Or maybe I just shouldn't tell you. I think I've learned now from now on not to trust you with my secrets. Yeah.
Yeah.
So there's an example of a situation where we need to keep things secret from our competitors. So although you and I earlier on we were working together, just then we were competing against each other. So it's a very simple demonstration, and this happens at all, like even in government. Like I live in England, you live in Northern Ireland, and it may be that your devolved assembly over there tells the government over here in England, but meanwhile, they're actually, do you know what, Abby, I'm going to play a rock this time, but maybe they don't play. So people do keep secrets from each other, not just in games that they're playing. Now, see the challenges, 1, 2, 3. We did super easy to begin with, and I'm watching the clock, and I think we've still got a little bit of time, haven't we? Have we got to like 3:50? I think we're doing 45 minutes or so.
I think so.
Yeah. And then there's some guy called Techno Teacher is going to come on and take us on a secret trip or a tour. So we could look at the middle medium task next, which is a bit more sophisticated. So we're in class. We want to send some more sophisticated messages to our friends. So, I've thought of something. So sometimes in class, it's the answer to a question. And the teacher might say, okay, class, today the question is blah, 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 blah. Is the answer A, B, or C? Like multiple choice. Okay.
Yeah.
So this time we're going to help our friend out. We're going to tell them, because we know the answer. So how can we tell our friend that the answer is A, but we don't want everybody else in the class to know that that's the answer? So what about if we just had the letter A displays on the screen and then our friend can see it? Would that work?
I think everybody else would know too.
Right. So we'd have to find a way of changing the letter A. Actually, that's starting to sound really hard. That we're moving into task number 3 or challenge number 3, because codes, like Abby, if you were driving along in a car and you saw an amber light in front of you, that's a code. Do you know what the amber light means?
To get ready to go or to
It
slow
does.
down.
It can mean get ready to go, or it can mean get ready to stop. How would you know when it's time to stop?
Because the red light comes on.
So they're codes. Now, sometimes people say, we're a code breaker. Well, actually, codes usually are just a very simple substitution where you take like a message like, Colette, I need help. Colette, make a distraction. So they're codes. But doing ciphers where you take plain text, like there's 2 words on the wall behind me. I don't think you can read it. It says top secret. It's not top secret. It just says top secret. But if I wanted to send a top secret message to somebody, I didn't want them to know, I could find a way of substituting other letters in place of them. So if we want our friend to know that the answer is A, what could we send them for A?
A picture or something, or maybe something beginning with A.
It could be a picture. Do you know, Abby, that many, many years ago, maybe 70 years ago, there was ways of sending messages over the radio waves using just noises? Did you know this?
I think so.
They used electrical pulses, and if you listen to the pulses, sometimes it would sound like beep, 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 beep. You know what I'm talking about?
Yeah.
So what's it called?
Morse code.
Morse code. So Morse code is a way of encrypting. Well, actually, it's not really encryption. It's a way of it's a code, because what you're doing is you take a letter, like the letter S, for example. I think that's beep, beep, beep. Yeah. Whereas the letter O is boop, boop, boop. It's longer, because isn't there a story about how the Titanic, which was built, was it built in Belfast? The Titanic.
Yep.
And it. We know it hit an iceberg, and they were sending out SOS messages on Morse code, and it was like, so what about if we sent Morse code in the lesson, like flashes of light for your friend?
That could work.
It could, as long as nobody else in the class knows what A, B, or C is in Morse code. So it could work. We probably need something a bit more sophisticated. So we'd probably have to do what they call a substitution cipher. So we'd have to send them a different letter instead. What about if we just sent the number 1? So the teacher asks, is it A, B, or C? And we know the answer is A. We could just send them a 1. How would that work?
It could work, but people might be able to tell.
It's a bit too easy. So we'd have to substitute it for something else. Now, have you ever heard of a Caesar cipher?
I don't think so. You might have to explain it.
Well, Caesar ciphers were used, we think, originally by the Romans. And all that you did was you did what was called a shift, where you would add a certain number of letters. So if we had a Caesar cipher shift of 2, and I wanted to send you the letter A, can you guess what that might be? To shift the letter A by 2.
C.
That's what the letter would be, because you move 2 places in the dictionary. Or what if it was -1, and I send the letter A -1?
It would go to the end of the alphabet.
It does. It goes
Z.
backwards. Okay. So what we could do is we could probably find a way to do that, a Caesar shift. Oh, actually, I should have read my notes because it's there in my notes. So can we do a plain text conversion using a Caesar shift? Well, we've only got 7 minutes left. Shall we go and have a look at make code and see if there's a way of doing that? We can at least explore. And then I wonder if people are watching this video, whether that's something that they may go and explore. Right. Now, I think that there is a way. The last time I looked at this, there's a way of displaying a letter. So could we find it maybe in basic again? And it says like show string. Oh, see where it says show string? Let's pull that across. Now, what happens if you double click on that block that we just brought in? Just double click on it for a moment. What's it say? The block is, it gives us some help or something. It says, well, it might just be when you hovered on it. Let's change it to the letter A. Oh, it says a letter or a word. So let's put the letter A in there. And you know how at the moment we have a pattern that if we, where is it gone? If we press A and B together, yeah. Can we swap them out? So can we put show string A in that box?
Right here?
Yep. So now if you press the two buttons together, it should display the letter A. Did it do that? Yes. Now, how would we do it so that if we wanted, if the answer is the message we're trying to send is A, the plain text, but actually the cipher needs to send C. That'd be quite cool in class, actually, because maybe everybody else goes, oh, the answer's C. Alan knows the answer's C. And actually the answer's A. Now, how would we do that? Can we do that in make code? There's a block. Go on. What do you think?
I was just going to say we could change the string, but that might be too easy.
Yeah. Well, we could just say change it to C, but then we'd have to find a way that if we mean A, it sends C. This is confusing. Let's see. Any other ideas? I was going to look in the math. You know, there's like I probably should say maths on it. Maybe designed it for an American audience. Remainder of. Is there something that's like +2? You can add.
There.
That block may help. Pull that across for a moment. So. Oh, does that fit in there?
Yeah.
Put it in. Yeah. I didn't know you could do that. Can we put the letter A in there?
Oh,
A. No.
I think it's going red.
Oh, do you know what? I think it's looking for a certain data type. Do you know what data types are, Abby? You do?
Numerical and characters.
Okay, what do we call numerical data types? It begins with the two letters that are the opposite of out.
Integer?
Integer, yes. So I think it's looking for an integer there, because you can only really add integers together, can't you?
Yeah.
I suppose you could probably add strings together with your letters. Okay. So maybe there's a way that we can mathematically add things. This is going to be, I should call this the hard challenge, shouldn't I?
Yeah.
Oh, actually, I think I did that already. So we need to try and find a way where we can shift or increment a letter by 2 positions. Do you think it might be in the advanced menu? What's in the advanced menu? Let's have a look in there. Functions. Oh, look, text. What's in the text menu? Is there something in the text menu? Length of split includes index. Oh no. Convert something to text. That do. Let's try. Let's put let's just try it in a block that when we put it in, when we press the 2 buttons together, it will show something converted to text. Will it let us do that?
Like that?
So we're trying to now convert 0 to text. So press the 2 buttons together. What do we get? Well, we got 0.
0.
To text. So it will take a number and convert it. Do you know, it might be easier to solve this problem rather than go A, B, C if it was just a number.
Yeah.
And if your friend always knew, if you could find a way to tell your friend what the shift number is first, and then Two. Yeah. I've got it. So, Abby, imagine I'm sending a message to you, and the teacher asked a question. Is there the answer A, B, or C? Now the answer is A. So what if I said to you, Abby?
Yeah.
I have to think about how to do this. -2, 3. Can you add those two together? -2 and 3.
-2 and 3.
Yeah.
That would give me 1.
So shout out 1.
1.
I'm going to be the teacher now. Abby, that is brilliant. You got the correct answer. And because what we did is we sent the shift first, and then we sent the answer. So your friend would just have to know that. Yeah, I think we've got something there that just needs teasing out a little bit. I am watching the clock. We've got about a minute. Abby, do you think you've actually learned anything in our workshop today? If we go back, what do you think you might have learned?
Definitely. I've learned how to do all this, and I've learned about the codes that they use called Inspector Sans.
And I bet the next time you're in somewhere like a supermarket or something like that, and you hear a message that says, because they do have codes. I used to work in a shop called Debenhams. Oh, they're not around very much. And they used to say in Debenhams, could all department managers contact the reception desk? And that was basically a secret message. Shall I tell you what the secret message is?
Yeah.
Actually, no, I don't know if I'm allowed to. I think you'll just have to I'll find a way of sending it to you in code later on. And anything else that you think you might have learned today that you didn't already know?
This, I didn't know that you could do and.
And these are called Boolean operators, where you can logically, you could say, if we have this but not that, or if we have something or something else. So some people call them Boolean operators or logical operators. Do you know what? I think we're out of time now, Abby. So Abby, thank you for working with me today. Thank you for being a good pal. And I think now a big hook is going to come over and it's going to pull one of us off the screen or something like that. And we're going to go on a secret tour.
Okay.
It's not happened yet. Do you think that they've forgotten that we're here?
Probably.
Thank you, Alan and Abby. That was a great intro to cryptography using MateCode. Now it's time for a short break with a pre-recorded super secret tour around a super secret location. Make sure to answer all of Agent Techno Teacher's questions and give yourself a mark out of 5, but don't put your answers in the YouTube live stream chat because your comments will be moderated so that everyone has a fair go at the quiz. Good luck, agents.
Interesting. Oh, hello. You can call me Agent Techno Teacher, codename Alan. So I've been asked to take you on a top secret tour of a location in the UK. One that has a very long association with code breaking and cryptography. Now, computers are part of our everyday lives. We use them regularly, and often we take them for granted without realizing. But do you know when the very first computers were invented? Do you think an inventor just woke up one day and thought, oh, I'm going to invent a computer today? No, that's not how it happened. We will find out how and why. But before we do, I have some questions for you. So I am going to be asking you some questions. Yes, you. So I'll share the questions with you in a moment, but you really need to think about the answers. So I'll read them out for you. And you probably won't know the answers yet. So you just need to think and guess and use your special powers. So, question number 1. What is the name of the very first computer? There's a clue here on the screen. It means something enormous, larger than life. Question number 2. So like I said, you need to think about the answers to these at this point. Question number 2. Where do you need to go to visit this first computer? So it used to be a highly classified secret. Question number 3. When do you think this computer was built? So I need you to think of the decade. So it may be that you know something amazing happened in history. So think of the decade. You could say like the 1890s or the 1920s or wherever decade you think. Now, question number 4. Why was this computer built? It wasn't just invented on a whim. There's a very special top secret reason why it was built. And it might surprise you to know for question 5, this computer is still being used today. A slightly different purpose. So how is it used now? What reason? And if you know where it is, that will help. So there's your 5 questions. Now I'm going to give you more clues because we're going to go and visit it and then we can see if you got your answers correct. So now what I'm going to do is I'm going to give you some clues. I'm going to take you on a tour. So we're starting in a car park somewhere. If you look around, well, you won't be able to tell, but we're not too far from the city of Milton Keynes. That's in Buckinghamshire. Now you might see some clues as to where we are. Car park looks a little bit empty, and that's because this is on a weekday when lots of people are still in school. Now these buildings, you might have seen buildings like this before. They were originally built to be temporary 80 years ago. And 80 years on, they're still standing. So they've actually survived very well. They were built to be inconspicuous, meaning difficult to spot from a distance, so that maybe if an enemy airplane was flying overhead, they wouldn't know that the buildings were there. So as we head down this corridor here, we go past the ticket desk and we're going to turn left because there's a special gallery in here. Now, this gallery, remember the questions I asked you. Number 1, I asked you, what is the name of the first computer? Well, in this gallery where we are now, there's some clues as to the other questions. And there's some things we're going to look at that you might think are actually a bit of a decoy or a distraction or a red herring. So can you see any clues here? I can see there's another language there. What's that say? Hard to read. And there's a keyboard with some buttons. And remember the question was, number 1, what is the name of the first computer? I asked you to guess the decade of when it was constructed or built. I asked you its purpose, where you might find it. So here's another machine here. Now this machine is also a clue, but I can tell you that this is not the first computer. It's the first of something, but that's not it. So now we're going to head down this corridor here. Again, this is just to help you with the clues. And on this corridor here, as we head down, there are some things that we can see. There's some bits of information on the wall. Not all of them will tell you the answer. Now, remember, if you're like a secret agent, maybe I could zoom in for a moment on here just for a few seconds. And maybe you can see something. It's going to disappear in a few seconds. You might not even be able to read it. And I'll just remind you, I asked you why this computer was built. And there's a bit of a clue in some characters or letters on this sign. So, further down the corridor, let's keep going. And you may see the name of the computer appear in a moment. So we're going to go into this gallery here. And we're about to see this computer. Come on. We're talking about. And there it is. It is huge. It's enormous. If I was stood next to it, so I am 6 foot tall, when I stand next to it, it is at least 1 foot taller than I am. It's got all of these lights and these other things called valves. It's got all of these wheels with paper that wears over them. Now, apparently, if you're to measure it, not only is it 7 foot tall, it is 17 feet long. That makes it absolutely enormous. And there is a word you can use to describe something that's enormous, and you might start to see the word appear in different places. So the reason we've come into this room is so you can look at this computer to see this is the world's first computer. And I asked you what's the name of it. I asked you where you'd need to go. I asked you when you think it might have been built. I asked question 4, why was it built? And question number 5, why or how is it used now? So that's the end of the clues. You might want to pause here, but now what I'm going to do is I'm going to start to share the answers with you. Okay, time to go through the answers. So this computer that we're looking at, its name is Colossus. That word can be used to describe something that is enormous. It was a set of 10 computers that were developed by British codebreakers during the Second World War. That's 1943 to 1945. And its purpose, well, it was designed or built to help in the cryptanalysis of the Lorenz cipher. So if you've never heard of Lorenz before, don't confuse it with Enigma, although it had a similar kind of purpose to Enigma. So Lorenz was a top secret code used by the German High Command. You probably couldn't get much more top secret. Lots of people have heard of Enigma code. Well, Enigma was used by officers, by infantry, people in the Navy and the Army, but Lorenz was used by the highest officials that were working with Hitler in the Second World War. Now, it was reserved for their most important secrets. Now, the Colossus computer that were built, they were used to help the Allies to gain access to a huge amount of encrypted high-level communications, so that the Allies knew what the German forces were planning in their attacks around the world. Now, this Colossus computer, this is actually a reconstruction or a rebuild, and it used thousands of these thermionic valves. I don't know if you can see them closely or not. They performed logical and counting operations. The paper tape readers that we were looking at before on the other side, well, they could scan up to 10,000 encrypted characters a second. Like if you were to measure the speed, that would be about 53 miles an hour. It could actually go faster. But what happened was the tape started to disintegrate and maybe even catch fire. Now, this computer, Colossus, it didn't actually have any internal data storage like your computer today might have a hard disk. And Colossus is regarded by many people as being the world's first programmable electronic digital computer. And although it was programmed using switches and plugs, not a stored program. Now, it was actually designed and built, some people say Alan Turing, no, Tommy Flowers, who did work with Alan Turing, but it was to be used at the Government Code and Cipher School at Bletchley Park. So you may know that Bletchley, in the county of Buckinghamshire, not too far from Milton Keynes, that was the home of the code breakers that were working there during the Second World War. It began, Colossus, it was completed on the 8th of December 1943, and it deciphered its first message just a few months later on the 5th of February 1944. So the design was based on the work of Alan Turing, but it wasn't built by Alan Turing. Now, the war ended in 1945, but Colossus and the reasons for its construction, well, they were kept secret for another 30 years. So it wasn't until like the 1970s or the 1980s that people started to learn about it. Nowadays, you can go and see it working if you go to H Block at the National Museum of Computing, which is in Bletchley, on Bletchley Park, and it's one of the working computers in the collection, and it's there to help visitors to understand how the first computers were designed and built. Now, there is now a 3D online virtual version of Colossus that you can use yourself. So, we're going to go back and look at the questions and see how you did. So, question 1, I asked you, what is the name of the first computer? Well, you should now know. Colossus. Colossus, 3 S's. That's very secret. Well, it's not so much secret nowadays. Question number 2, I asked, where do you need to go? Well, you could say England, you could say Buckinghamshire, you could say Bletchley, but the best answer you can give is Block H in the National Museum of Computing. Question number 3, I asked, when do you think this computer was built? So you just had to think of the decade. Well, you could say in the 1940s. So it was finished in 1943 and it did its first code breaking in 1944. I asked why this computer was built. Well, the simple answer is it was built for code breaking purposes. But the best answer you could give was it was used for cryptanalysis, used to decipher the top secret code called Lorenz. It was actually a cipher, not a code, that was being used by the German High Command in the Second World War. And question 5, the final question I asked, how is it used now? Well, it's an exhibit, but it's not one of those exhibits in a glass case that doesn't move. You can actually go to the museum and you can visit it, and you can also see a virtual version being used online. So there we go. How did you score out of 5? Well, I bet if you were to do this again, you'd probably score 5 out of 5 the next time. Thank you.
Up next, we'll have Kevin and Charlie. Kevin runs a video games company, and Charlie, Kevin's daughter, is a regular jam attendee with her dad. Kevin will be taking Charlie through a workshop on ciphers in Python, so this is a slightly more difficult level activity for everyone at home. Just a reminder though, that all our worksheets will be made available online and as available as links in the YouTube live stream chat. We have a secondary stream still going for the Bitbot drawing activity if any of you are interested. All of today's activities are also still listed on workshops.niraspberryjam.com/public_schedule. But with that, and with both links on the live stream on that website, but with that, we'll leave it to Kevin and Charlie.
Hi, everybody. My name's Kevin. This is Charlie. As they said, we're allowed to be standing next to each other because we live in the same house, which makes it really easy for me to help Charlie out when it comes time to doing some code. As you heard from Sam, we're going to teach you about coding ciphers in Python. Now, if you were here for the first session with Alan was just starting to get into the idea of ciphers, of letter substitutions and things like that. And that's the kind of thing that's really easy to do with computers, provided you can figure out what the algorithm is. Algorithm, stick with me. It's a word that's going to be used quite a bit during this. It pretty much just means formula. It means doing a bit of math, making letters do other things and substituting them for other things. First of all, if everybody at home can see what's on Charlie's screen, if you're in REPL right now, in fact, if you're not in REPL right now, I believe it's nij.am/join-REPL, REPL. When you get into there, you'll have to give a username and a password. Don't use your real name, please. And then you'll get into a list like what Charlie has here. If you can see her screen, there are 5 sections: ciphers 1.1, 1.2, 1.3. Charlie, can you open ciphers 1.1 for me?
Go.
Go for it. Yep. Confirm. Sounds good. Yep. Allow it.
Okay.
Okay. And then on this side, switch to main. Okay. So what you should see, if you've got a screen up like Charlie's, you've got main.py over on the left. That's where we're going to be doing our coding. And on the right, you'll see in big letters, what is a cipher in Markdown. Also on the right, there's a little tab that says console. I'm going to be coming back to that in a minute. So when, to use the word difficult, it's not as difficult as it sounds. We're just going to be, if you know your way around Python, you understand a little bit of coding, like what we've been doing with the bitbots. If you understand for loops, if you understand variables, taking in something and printing it out on screen, that's pretty much the level of all we're doing, plus a little bit of maths. So to discuss the idea of what's a cipher is a substitution. The difference between a code and a cipher, those two words are kind of used interchangeably. Code is kind of like what Alan was doing before. Alan said, well, let's make this picture of a tree represent I'm in panic mode. Or let's use this bird to represent what was it?
Distraction.
Distraction, yeah. Or if I were to speak in code like Inspector Sands, or if I say the eagle has left the nest instead of the president has left the White House. It's the sort of thing that people will hear the words and translate the whole word. But a cipher is about taking the letters of a word and swapping it out so it all looks like gobbledygook unless you know how to decipher it, unless you know how to unlock it. So just in terms of theory, have you got, Charlie, do you know some ciphers? Like, for example, lights and sounds. A cipher that is used to do lights and sounds. Is transmitted through lights and sounds. Alan mentioned it on the Titanic.
Morse code?
Yes. Morse code is a perfect example. An A is a set of sounds. A B is a set of sounds. And if you don't know what it is, you just hear a bunch of beeps, 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 beeps. Doesn't mean anything. But if you can unlock it at the other end, you decipher it by the sound. Another one. Have you ever seen the one that's done with flags? holding flags up
with
in
chips and
different
stuff, yeah.
directions. Yes, that's a substitution cipher because I don't know it. It's called semaphore, but you can send visual messages a long distance by holding a flag in this direction. Like that may be a C and that's an N and that's a whatever it is you're spelling. And it's on the positions of your arms. Symbols. Sometimes you'll see just a bunch of random things or somebody's written alien languages or use Wingding's font. That's an easy one. It's just, it still makes sense as long as it can swap back to something we all understand. So, what we're about to do is, in these substitution ciphers, the best way of going about this is you need an algorithm. You change letters into numbers, then you do something with the numbers, and then you turn them back into letters. That's the 3-step process for doing a cipher inside of a computer. You can do it randomly. You can do cryptograms. You can just say, I'm going to decide that A is going to equal a dog, and B is going to equal the letter X, and C is an @ symbol, whatever. But you're better off, in a case like this, having some kind of a formula. So, scrolling down on the side of Markdown there. Yeah, so you get into, there's a number cipher there. You see 9, 12, 15, 22, 5. That's numbers have been substituted for letters. The 2 below that, they just look like somebody fell asleep on the keyboard. But if you can unlock it, you can read what it says. So going down a little bit further, it says for each letter in the message, I hope everybody's in Ciphers 1.1, by the way, if you want to follow along. But changing a letter into a number, you're going to need a command. It's ORD and a set of brackets, a set of parentheses. Charlie, will you please go into the console for me? There. Now, right in here, you can type a command and see what answer comes out. But ORD, put a open bracket, single quote, and then a letter between A and Z. Capital, please.
Go G.
G. Okay. Close the quote, close the bracket. Okay. Hit it.
Enter.
What do we get? 71. We have a number. Will you do ORD F for me?
Open bracket, single quote.
Capital F.
Oh, yeah.
Yep. There you go.
And then enter.
And that's 70. Do ORD H for me. And that is predictably 72. So what we learned is that the computer organizes the alphabet in alphabetical order. Thank goodness. Where does it start and where does it end?
So will I do ORD?
Do an ORD A and an ORD Z. A is 65, and give me a Z. $90. Okay, so A is 65 and Z is 90. We could make this more convenient in a minute, but first I just want to mention that ORD does not only do capital letters. 65 to 90 of the A's to Z. If you were to type in, go ahead, Charlie, ORD, and then quote the number 9. Yeah, 57. What about a lowercase letter, like, small I? 105. Nice. Okay, a symbol of some kind. I don't know, an @ or a question mark or a pound sign, something like that. What do you got? An ampersand.
38.
38. Okay, so what these numbers are coming from, they aren't random, obviously, because we got that nice 65 up to 71. The letters of our alphabet go from 65 to 90. That's capitals. Give me a lowercase a and an uppercase a as well. Or, sorry, a lowercase a and a lowercase z as well. Yep, 97.
And then...
And that goes to 122. Okay, so these things, I'm going to break away for a second for the advanced word here. It's the ASCII table, ASCII. And if you look up ASCII table on like a Google image search, it'll show you a big old dump of all the letters, all the characters that the computer stores as a number so that it can easily swap it out, ask for them later, call them up, and store everything because it loves its ones and zeros. Computers loves everything to be dropped back down into a number. In fact, I think there's something in Markdown Pop back into Markdown. Changing. Oh, no. We got a bit more to do first. All right. So this is all of us going through ORD. ORD takes a symbol, a character, and it turns it into a number. Now we need to flip that on its head. Where we want to take a number and we want to find out what its letter corresponds to. And that is something called CHR. Okay. So CHR. Yep. CHR, put a bracket. This time no quotes because it's just a number. 71. And what do we think the answer is going to be?
G.
It's G. So, ORD G is 71. CHR 71 is G. It's a table. It has a one-to-one connection. So, you imagine CHR 65. It's going to give us A, and CHR 90 is going to give us capital Z. Wonderful. This 65 to 90 is where we're going to work with most of this session. We're just going to work with letters. So, as I said at the beginning, to do a cipher inside of a computer, inside code, we have we want to change our original message into a bunch of numbers. Then we want to mess with those numbers, and then we want to turn the new numbers back into letters. So we've covered step 1 and we've covered step 3, and the last thing to do is the middle, the maths. So pop back into Markdown again there, Charlie.
There we go.
And keep scrolling down. Well, I've got that nice little bit. Oh yeah, the ASCII table. I've got something in there for anybody who wants to try it. We're going to skip it for now. But there's just 2 lines there. It's a for loop that allows you to see what all of the ORD and CHRs work in from, say, 32 all the way up to 255. Okay? But doing some maths, aka the algorithm. From the examples shown, we already know that A is 65. We won't move our way forward. We've got a little table there that shows A65 all the way to Z90. But what we'd actually like for our first cipher is a simple number to letter substitution cipher. We'd really like A to be 1, B to be 2, C to be 3. So what you have to do in the math section in the middle is you get the ORD of any letter, and then you have to do something to it that is the same across all the letters, and then turn it back out the other side. So in this case, I've asked the question, what algorithm can we apply to 65A to make it into 1, 66 to make it into 2, 67 to make it into 3, 68, 4, 69, 5. It's a difference of, Charlie,
64.
easy. Yes, that's a didn't want to put you on the spot there, but the answer is right away. Okay,
64.
Answer is subtract 64. So we get our number, we subtract 64 from it, and then we put that number on screen, and we've got our first example of a substitution cipher. Right? Now, the first one, I knew this was going to sort of start graduating in terms of difficulty, but all the code is already in this session for you. So if you want to try this one out for a little bit, all you have to do is press run at the top of the section there. Hit run. And we've got ourselves a nice easy A to Z substitution cipher. So to encode the letters into numbers, you're going to hit 1. Oops. Yep. Just to show you how fast you can get this to work. Now we're going to enter a message in capital letters. Hello world. And what does it do?
Enter, and it gives me a string of numbers.
And what are, yes. So to anyone looking at this, they'd go, what is this? Is this a license plate? Is it a phone number? Is it a date? Is it a set of coordinates? What is this message all about? It turns out the message means is so trivial that it's almost not even worth decoding. But we're going to do it anyway. Can you copy that set of numbers for me? Yep. Oops. What happened there?
No, just
Keyboard
says
interrupt. Interesting. Try another.
That's probably
Did
okay.
you actually copy it?
Yeah, I think we.
Oh, wait, reselect. Huh. Let's see what happens. Okay, 8, 5, 12, 12, 15, 23, 15, 18, 12, 4. All right, let's run.
I'll just make sure.
There we go. Okay. Hit run again. This time we're going to decode.
Okay, so number 2. And then enter.
Yep. And now we can enter a string of numbers. Now the numbers need to be separated by spaces, and the spaces need to have that dash in place, because that's the only way this. If it doesn't do that, if you've typed it in slightly wrong, you're going to get some kind of an error. I didn't bother to error check all this, but I wanted this to be readable. So go for it. Bang.
And we can see the message.
That's right. And the message says, hello world, just like we typed it in the original set. So as you can see, ciphering, you jumble up the letters into something else, somebody else receives it, knows how to unjumble it, and it becomes something that does make sense again. Just to look at the code for a second, it's not, let's see, what have we got here? Let me just drive for a second here. Right, so the encoder, obviously print is enter a message in capital letters. You know how to print. Message, we get the input. So this is where we get the information that's coming through, pardon me. The cipher, the message starts off as the full set of letters. The cipher starts off as an empty string. Well, that's why we just put the 2 quotes there. There's nothing in it. And then we do a very simple for loop. For every letter in this message, we want to first get the ord of that letter, and we want to subtract 64 from it. That's it. So we've got an A, we subtract 64 from it, it becomes a 1. Sorry, we turn it into a 65, it becomes a 1 when we subtract that. And then those last 4 lines, if letter equals space, cipher equals dash, else cipher equals the number. That is to ensure that spaces are not converted. We're only converting the letters in this thing. So if it's a space, put a dash in. If it's not, just give me the number. And then print it out when you're all done. Okay, that's very readable as far as I'm concerned. And the decoder is the same thing in reverse. Almost. There's something slightly different. It's that list equals cipher split. And the reason for that is because we want to treat the numbers like numbers. The number 20 needs to be a 20. It can't be a 2 and a 0. If you know what I mean. Mm-hmm. It's not 2 separate things. So what the split function does is it splits everything up by spaces. So then you've got yourself a list of numbers. It treats it like numbers with that extra int, which is down here in message number int number. It's treating that number like a word, but you turn it into an integer, and then it adds 64 to it. And now we got our original message again when it does the CHR to pop it back up. Okay, so that goes back to our originally 3 steps. Letters into numbers, mess with the numbers, turn the numbers back into letters. Right, that's part 1. That's just an intro to how this stuff works. So now, Charlie, if you can go up to NIJam Live, at the top there. Yeah, right there. And pop back out. And next one, you're going to go into 1.2 at bash. Okay, now, the at bash, put this one onto main.py. Yep. Okay, what you'll see, don't be scared. We got a blank space to code in, but over on the right, we should have this at bash cipher help the worksheet. Now, at bash, that is a back to front. It's a, many of you may have seen this before, or if you haven't, you should have invented it by now, but the idea that A is Z and Z is A. B is Y, C is X, right? We just take the whole alphabet on top, we write the whole alphabet in reverse underneath it, and we've got ourselves a code that still looks like gobbledygook. If you look underneath there, I have the word banana that's been transmitted, it's been encoded into yizmizmiz, which is fun to say on its own. Almost as fun to say as banana. All right. So what's great about this code is that encoding it and decoding it is using the exact same code, right? A becomes Z's, it becomes unintelligible, Z's become A's, the word becomes readable again. I'm going to get Charlie to just start typing this straight in and see how this goes. Yes. Line 1, ask the user for the message.
Input.
So, yep. Keyboard layout's different, isn't it?
Yeah.
Okay, so line 1.
Enter a message?
Yeah, leave a little space there, so,
yeah,
and then maybe a
my
little colon.
Oops.
There you go. Not essential, it's just the enter message, but it's
So it
just
looks
neater.
nicer.
Right. So our message we're going to receive, you keep on going, I'll talk over
Okay.
top.
Now line 2.
Yeah. So first thing we're going to do is receive the message from the user. Next thing we need is the place where the cipher message is going to end up. That cipher equals, it's just 2 quotes. Again, starting with an empty string, because we're going to pluck one letter at a time and convert it and then drop it into the cipher. So if we were doing the name Charlie, it's going to pluck the C, it's going to turn it into an X, and then that's going to go into the cipher. And then the next one's the H, we're going to turn it into a maybe an S, I'm not sure, we'll figure it out. Plunk that down into the cipher. Okay, so now we got a for loop. That's the third thing. The for loop is the, we're going to do this one letter at a time. With each letter, as I said, turn letters into numbers, which is what Charlie just did. Number equals ORed letter minus 65 this time. Why 65? I'll talk a little bit about that. Computers like it when the first number of a list is 0. We like it when it's 1. Computers like zeros. So in this case, we're going to work with a set of numbers where A is 0 and Z is 25 instead of the 1 to 26. So next thing Charlie's going to do, she's already done it. At bash number is equal to 25 minus number. Now, that is the algorithm for this set. If you go to the bottom, you can just carry on if you like. Okay. If anybody's curious as to why 25 minus number works for this, I've added a little bit of extra reading at the bottom of the markdown section on the right. It's basically the process of how you might work out an algorithm. Now, this is a very specific algorithm of an @bash. If you say @bash, people will know what you're talking about. So if you yes. At the bottom of all this, we've got where we're starting, turning an A into a 65, and where we want it to end up, which is 90. And then it sort of takes you through the process of turning the 65 into a 0, and we want it to be a 26. And then if doing all these different things with it, we end up with the number we want that works as a formula pretty much the same way as the last cipher that we did. How we doing there, Charlie?
Pretty good. I'm almost done with it.
Pretty good. You're on the second last line. Yeah, so talking you through that, unless you're in the midst of typing it through at home.
Okay.
Right. Oh, and don't forget to print it out at the end.
Yeah.
Oh. Yes. Okay. Yeah, I realized you're supposed to be. Yes. Go ahead and finish that, and we're going to learn something from it.
Print.
Cipher. Now, as you know, for Python, your indents are very important. If Charlie was to run this program exactly as it is right now, we'll see something interesting happen, which isn't exactly right, but it'll do a fine job. Yep. Okay, so entering a message here. We're just going to say hi. Now do something slightly longer.
Oh, okay.
Yep,
Sorry.
run it again.
Okay.
Charlie, bang. Now, because print cipher is indented under the else statement, every time it adds a letter to the cipher, it prints out the whole thing. What we'd rather do is print it only once when the whole thing's finished.
So do I just...
Oh, one more. That's it. Okay. This time we should only get the end. Hey, I was right. It's an S. Uh-oh. Uh-oh. What have we done? Line 1. Invalid syntax.
Just try it again.
It was something to do with this. I know. Wait. No. Keep going.
Oh, there we go.
Oh, that worked. It was
Just
just it
like
had a
you.
problem with me. Okay. So Hello PyJam has given us, a bunch of gobbledygook. Now, copy that gobbledygook, and you'll see that ciphering and deciphering, coding and decoding in @bash is the exact same bit of code.
So we just
Run it again, and you enter the original this message again,
Oh,
and we get Hello PyJam. Bingo. We're back. I think at the bottom of that markdown area, there might be a stack of things to try. There you go. You can try
Let's
decoding
check it.
some of these messages. You want to give it a shot, Charlie?
So, should I just copy this?
Yeah, copy that.
Yeah. Copy. Console.
Run it again.
Dear Agent Pi.
Oh, this is getting good.
Okay. Let's see. What do they have to say to us? Agent Mulholland cannot be trusted.
Ooh.
Okay. Paste. See, he has cookies but will not share with me.
Last one.
Copy. Let's see. What does it say? Paste. He must be taught a lesson.
Oh,
Oh
okay.
my.
Right. So there we go. We've just received a secret message. It's in @bash. Our code works for it. Everything's great. Charlie just typed that in right off the page. Nice. Okay. So you have now learned the A1Z26 cipher. You have now learned the @bash cipher. Third one we're going to go to is the Caesar cipher, which was just mentioned in the previous session. And yep, there you go.
So
Down, down,
what
down
do
into
we-
1.3. Lovely. Caesar, as opposed to taking the alphabet and turning it on its head, we're going to take the alphabet and we're going to push it a little bit to one side or the other. It's got a shift. Okay, so a Caesar cipher, if we say the shift number is 3, A becomes D, B becomes E, C becomes F. You can have a shift number of whatever you like, and it really helps if you're the person on the other end who has the shift number in order to decode it. So, what have we got here? Main.py, pop over here. We've got some assembly, an almost finished bit of code here, right? You'll recognize most of it. First part of it is the entering the message. The middle bit is do this to every letter. The last bit of it is the bit about spaces and skipping, right? And finally, that Caesar letter. By the way, make sure you spell Caesar correctly and the capital L when you're copying this stuff over, because I've got a something on line 14 there. That's the variable that is waiting for. Okay, so coming at it from the markdown side, where it says shift goes here, what we're going to do is we're going to ask the user for a shift number. So go ahead and find that bit on the right and see if you can paste it into the stuff on the left.
Is it 4-letter and message?
Nope, that is the code that you're already looking at.
Oh,
if you
yeah,
scroll up a bit, where it says shift goes, no, down a bit, sorry. Where it says shift goes here, you're going to ask the user for a number. So the shift equals an integer.
Input.
Leave a space. There you go. And now the algorithm is going to go below.
Okay.
So this one, the idea of the last one, we had to have that 25 minus the number equals the translation of that number. The algorithm in this one is actually really easy. It's just if the shift number is 3, then we take A, we turn it into a number, we add 3 to it. If the shift number is 8, we add 8 to it. If the shift number is -7, we subtract 7 from it. But there's a trick. And while Charlie types this in, I'm just going to make mention of a little known, well, it's well known for programmers, but it may be the first time you've seen this thing if you're new to coding. And it's using the percent sign as a mathematical operator. So you would go, say, for example, 7 plus 3, and you'll get the answer of 10. 7 minus 3, you'll get the answer of 4. 7% 3, you'll get the remainder of when you divide 7 by 3. Okay? So what I mean by that is if you divide 7 by 3, you'll get one group of 3, second group of 3, and you'll get one left over. That's the remainder. So And I realize I'm talking down to some of you, but some of you, this may be the first time you've encountered that session. If you're experienced programmers, then please feel free to just soldier on with this. But it's called the modulus function or the modulo function. So what it's really handy for is if you've got looping lists. When you're doing something like this, where we want A, B, C, D, E, F, G to go all the way to Z, but then also we want the Z to loop back around to A, you use this percent symbol to figure out what number it would end up at between 1 and 26, or 0 and 25. Okay? I'm not sure if I overcomplicated that too much, but the basic idea is when you if we're adding 3 to everything, it's easy to add 3 to an A and get a D. But when you get all the way down to Z, you don't want to add 3 to it and end up with some weird random symbol. You want it to jump back to 0 and count up from there. So that's what the percent sign is for. There's a little more on it at the bottom of the session. So what do we got here? Caesar letter, Caesar number. It looks like we're ready to go.
So should I hit run?
I think you should hit run.
Okay, enter a message.
Yeah, you're not typing? There we go. We'll do another hello again. No, hello agent Mulholland.
How do you spell his last name?
Oh, it's MULHOLLAND.
Thanks.
There we go. What is our shift number?
Let's
What are we
go 6.
6. Nice. Okay, so NKRU. It looks like just a bunch of gobbledygook. Grab that. There you copy.
It's what?
Is trying. Oh, come on.
Okay, I think I've got it.
Have you got it?
Oh.
Okay. Hit run again. Enter the message. Oh, interesting. Yep.
Yeah,
Well, let's hope that's the one.
maybe.
Maybe.
And then how do I get it in?
Oh. Weird.
Don't know how to use this computer. Yes, I'd like to use that one.
Interesting.
Should we
Hold
just do
on.
it again?
Uh,
We'll do a different message.
okay, try again. Yeah.
We'll just do...
Okay, try again. Shift number 5. Okay.
MJQQT.
MJQQT, but keep it anyway. Okay, there you go. MJQQT is the message we want to decipher.
And shift number. I'm going to use the same shift number 5
Yep.
that I used before.
Yep. Oh. Anybody figure out why they didn't work?
No.
Hey? Because we shifted forward 5, and then to decode it,
We
you
can't-
shifted
yeah,
forward
shift
another
another
5.
five,
So how do
yeah.
you decode it?
I think you'd have to use a minus number because then you're going back in the
Yes.
alphabet.
There you go. Give that again.
MJQQT.
The shift number this time
Negative.
is -5. Hey, nice. Right, that is right. Have a look at the markdown again. I think there's more secret messages down the bottom there.
I think...
Is there? Oh yeah, we got a couple there. It says you can see the message. Yeah, raspberry jam with the shift number 3. You can try decoding those two right there.
Okay, should we leave that to...
What's that? Well, I don't know. Did we do those ones? Give it a shot. Try that first one, but leave the second one.
Yeah.
I think. Are you right clicking or are you double clicking?
I'm double clicking.
Try right clicking on that edge. There.
Alright. Enter
Okay,
a
enter a message.
paste.
Paste.
Do you remember
And
what the
I think it was
13,
minus
I think. I think
13.
it was just 13. The second one is -8.
Actually, 13 or minus 13 shouldn't matter. Go for it.
The password is avocado.
Nice. Okay.
And then we'll leave the second one so we don't want to ruin that.
That's right. Yes. For anyone, if there's anyone on the live stream, that one's for you guys. Now, again, down the bottom of this one, the advanced section, where did we get the algorithm from? If you like maths, if you like figuring out puzzles, just work out how we would have got that. But you can see where the modulo operator comes in handy is when you're trying to turn something that's 25 into 0 and 26 into 1 and 27 into 2. We want it to loop around so that we're talking about remainders, not decimals. Okay. That is cipher number
3.
no, 3?
Yeah.
3. Yes, 3. Nice.
No.
We got
Let's go
right.
back.
So, we got one more little thing to talk about here. We actually had 2 suggestions, but yes, ciphers 1.4, cracking Caesar. Okay. Now, Caesar, because it's a shift, they are notoriously easy to crack. You know, they may have fooled people back in the Roman times, but nowadays it's like, especially with a computer, but even on paper, you can puzzle your way through this in a pretty easy set. Now, I've put a little bit at the top here. There's a little bit of reading that you can do at the top of this markdown session. They'll just talk to you about how you solve anything like this, like a puzzle. I'm sure Alan touched upon it a little bit in his session where we in fact, we were talking about having like Bletchley Park, the Enigma code, that these were puzzle solvers. In fact, the way they recruited people to come in and do code cracking was they would occasionally put out puzzles in magazines. And then, you know, call this number if you have solved the puzzle. And anybody who can solve the puzzle might have got a call from the government to say, come on down and see if you can help us crack these codes. It's, you know,
It's really cool.
it is really cool. It's like, and there's been movies made about it for real. There's been like,
and would it be like proper codes? Like
it would be,
proper ones you'd have to crack,
well,
or-
I think they still do it. I think I can't remember the name of the society. Well, it's probably the National Cipher Challenge, but they do occasionally put out these Christmas puzzles, or they slip things in. Like, you know, obviously a lot of the big number crunching is done straight with computers for encryption nowadays. The idea of the old electronic wiring that causes one number to light up when you press a different number, that was there's some amazing bits of engineering. We haven't even talked about the Enigma yet, unless Alan did. I may have missed that bit of his. But yeah, the idea of cracking ciphers like a puzzle, it's a game. And if you treat it like a game, you can actually have a lot of fun with it. Now, unfortunately, with the Caesar cipher, the game is very easy. And the reason for that, like I said in here, I talk about, like, you could do letter frequency. You know, the letter E shows up a lot more than the letter Z. Words like the or and will show up more than other 3-letter words. So you can look at that little 2-line block of code that I've added in there, and I've said already, well, there's a couple of patterns here you might want to explore. I don't tell you what the answer is. I'm just going to leave that for anybody who wants to work that out. So scrolling down the markdown side a little bit more, cracking a Caesar cipher, the easiest brute force way to crack a Caesar cipher. Charlie, come on, it's not that hard. What do we do?
You just test all the answers?
Yeah, there's only 26.
Yeah.
So yeah, if somebody's shifted the alphabet by 3, the maximum they can shift something is 25. And what comes out the other end, if all you do is just try a chunk of it and see, does it work with 1? Nope. Does it work with 2? Nope. 3? Nope. 4? Nope. 5? There it is. Shift number was 5. I've got the whole message. So if we can modify what we've just done, as you can see, this code in this section is exactly the same as what you just did, but we're going to change it so we don't ask for a shift number. This is going to be specifically a decoder. So replace the shift number section there with...
So delete?
Yeah, delete that whole line. And instead of asking for it, we're just going to feed 26 shift numbers in succession. So for shift is going to be the variable that holds the number, and it's going to do it from a range of 0. It says 0 to 26. What that means is 26 numbers, which means it will end at 25. Okay? And then you need to take everything below for shift in range.
So all of this?
All that. And you need to select it all and hit tab. And that will make sure that everything in there is going to be done 26 times. Finally, it's not essential, but you can change that bottom line where it says print cipher to say print shift.
Oh, that is not how you
That's
spell
not how you
shift.
spell shift. Watch when you type in that. Shift, comma, and then a little space or quote.
And
And then another comma.
Is it a space? No.
It's okay. another comma, and then the word cipher. All we're doing there is we're labeling them. 0 gives you this, 1 gives you that, 2 gives you that, if you're curious exactly what number it's going to shift. And now, grab one of those bits of code down below there to test.
Let's go.
So,
Let's go from the top.
Yeah,
This might
copy
be
that
another,
guy.
Might be another bigger message.
Nice. Run it.
Run.
So we enter our message. And what we get,
Okay, this might take
0
me a
through
minute.
25. Scroll your mouse down so people can see where your eyes are going. Yeah. When you get to it, highlight it.
Oh, here we go.
Nice. So the shift in this case was 22, or it was 3, and now it's -3, maybe 4. I'm not sure which.
Okay.
Okay.
So we've got a first one. Dear Agent Pi.
Dear Agent Pi. Let's try the next one.
Okay. Copy. Okay, run again. Enter message. Paste. Okay.
Ooh, longer.
It says your contact in Moscow. Your contact in Moscow is Agent Stewart.
Ooh,
Okay, we're gonna do the
the
first.
plot thickens. You can
We'll do the first 3, and then we'll.
Yeah. Oh, yeah. Do the first 3. There we
Yeah.
go. Yeah. So as you can see, what Charlie's doing here, she's going to check out the third one. But like I said, Caesar's easy. If we know it's a Caesar, we just shift until we get the right answer. What do we got here?
Okay, when you see him, speak the following code phrase,
Right.
and then we'll leave you guys on a cliffhanger, so you can
Cliffhanger.
you can
All
do
right.
that.
Now, I mentioned a little bit earlier the Enigma, right? Now, the Enigma was ridiculously hard, and it could not be hacked without the invention of the computer. It was one of the things that drove the invention of the computer. But they tried to crack the Enigma with same with the puzzle solving, brute force. Let's see what words substitute for which other words. But it was it was a beautiful piece of electronic equipment. It had rotors, and these rotors connected letters to letters and wires to wires, and the rotors could be rotated. It could be assembled in different ways. They could be swapped around. They had cables, so you could today plug A into G, and when you press the A on the button, it thought it was a G and sent it through the system, and it came out the other end. It was an amazing piece of machinery that created, it's something in the quintillions, the number of different ways that you could assemble this thing meant it was essentially uncrackable. But we did crack it. I say we, it wasn't me. It was cracked. It was, in fact, I don't know how old you all are watching this, but the movie The Imitation Game is absolutely fantastic, and it talks about that whole process. You'll have to ask your parents to watch that if your kid's on this, because there's some pretty serious stuff in there, obviously. But the actions that they took, and the abilities of this fellow Alan Turing to invent the machine that would try one letter at a time, a number of different dials, and running it through it like this, allowed them to eventually crack what the Germans thought was an uncrackable code and use the information they got from it to win the war by prodding things in different directions. Now, after the invention of the computer, a lot of that electronic stuff kind of went out the window, but it's still heralded as one of the greatest cipher devices out there. And actually, not long ago, I coded a working Enigma machine in Python. I'm not going to get you guys to do that, but I got it to work. And Sam's looking at me because I also coded one in Redstone. So, and I'd love to show you that. We should have that on the live stream. But I've got one more assignment for you here. And it's an assignment that I'm not going to give you any coding help on. It's more of a takeaway. If you found any of this interesting, I wouldn't mind it if you did a little bit of extra work, looked into it a little bit further. All of the information deeper than this, deeper than these one pagers that I've put together. It's all on Wikipedia. More ways on how to open up these codes and different types of codes. But first, pop out of there, pop into Ciphers 1.5, and I'm going to tell you about. Says if you liked Caesar, you'll love Vigenère. And a Vigenère code, if you read through this advanced cipher challenge, it is a way of shifting the same way the Caesar shift works, but according to a passphrase or a passcode. You give it a word. So instead of in Caesar, where it was saying, take the name Charlie and move the C over 3 and the H over 3 and the A over 3 and the R over 3, which is easily crackable, I could say, take my message and use the passcode as Charlie. And in the first one, it'll shift it over 3 for the C. The second one, it'll shift it over 8 for the H. And then it'll shift it over 1 for the A. So it's like underneath your whole long message, you write Charlie, 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 and you add those letters together. So that's the assignment I want you to take away. See if you want to code any more. You can do it all here in REPL and just try it out. But yeah, like I said, if you love Caesar, you'll love Vigenère. Oh, one final message. I know I'm running over just a little, but in the last 30 seconds, if any of you out there have Disney Plus, I highly recommend a show called Gravity Falls. If you watch Gravity Falls, at the end of every show, in the credits, you'll see a random string of letters and numbers. Every episode of Gravity Falls has a code in the credits that you can crack with these 3 ciphers that I've just taught you. So, if you don't want to code yourself a Vigenère, go watch some TV. All right, I think that's me. That's Charlie. Thanks very much for listening in. I hope you enjoyed it. And who am I passing this back to? Or am I running straight into the next thing? What's happening?
From one segment with Charlie to another, this time Charlie will be interviewing William, who is a regular jam attendee and a code-breaking expert. William completed the National Cipher Challenge and won the Ada Lovelace Prize of £1,000. In the interview, they talk about how William went about breaking the ciphers, as well as how you can get involved with the National Cipher Challenge at home.
So my name is Charlie Beamers. I'm 14 years old and I've been attending the NI Raspberry Jam for about 3 years now.
And I'm William. I've also been attending the NI Raspberry Jam for about 3 years as well.
William and I and a few other Raspberry Jam regulars have worked together in previous years to compete in robotics competitions like First Lego League and Pi Wars. Today's jam is all about cryptography and code breaking, and I'm interviewing William today because last month William took part in the National Cipher Challenge. William, do you want to tell us a little bit about that?
Absolutely. So the National Cipher Challenge is a challenge organised by the University of Southampton. It runs over about 3 months. This year it ran from September to December, and it involves breaking classical ciphers.
So what sort of challenges did you have to complete? And can you maybe kind of explain one of the challenges and how you went about solving it?
Sure. So one of the earlier challenges was a basic substitution cipher. So one of the main techniques you can use to solve classical ciphers is frequency analysis. And you can spot that it's a substitution cipher by noticing that the frequencies of letters are very similar to normal English except in the wrong places. So you could either write your own tooling, or you can just use one of the many online tools available to solve the substitution cipher.
Did the challenges have any sort of like specific themes, or was it just a bunch of different challenges you had to do for code breaking?
Yes, they all had a theme of World War II and breaking Nazi messages, and they had a section on the website that had a lot of old cipher machines on them, and it was also really interesting just to see the old classical ciphers and what tools they used to encrypt their messages.
That sounds actually really cool, yeah. Do you think that having the World War II theme made coding more interesting?
Yeah, I think having an actual storyline to it made it a bit more interesting than just, here's some ciphertext, go crack it.
Yeah.
I think it made it a lot more interesting because there was actually a plot you could somewhat follow.
How long did it take you to complete the competition? Or like about how long did all the challenges take?
So the challenges were released every week at a certain time, and I completed most of them in about 10 minutes, but the last one, which was kind of hard, it took about 2 hours to complete. So overall about 3 hours in total.
Were you completing them faster than other people, do you think? Like what was the time limit to complete them?
So you were given a whole week to complete them, but you were given less points if you completed them, say, a day after they were released or 2 days
right.
after they were released. So speed was a very important factor, and it did, at the end of the competition, with the final challenge, you did have to complete it within the day to even stand a chance at winning anything, really.
And that's when they took you the longest?
Yes, that's the one that took me the longest.
So how did you get involved in the competition?
So I heard the competition through some of my friends, and I also saw it on Twitter. So I decided to give it a go and see what it was like, and I did not expect to win it, which was a nice surprise.
How much knowledge of coding or cryptography do you need to enter? Like, do you think anyone could enter, or do you need to already have quite a high level of understanding of it?
So for the cryptography side, I think you don't really need that much cryptography knowledge, because on the website they provide a lot of good resources, such as guides on how to use different strategies to crack classical ciphers, and they also provide some tools to do that for you. There's also a really good forum on the website that you can ask about classical ciphers and how to break them. So I think on the cryptography side, they have really made breaking classical ciphers really accessible, and I think that's a really great thing. For coding-wise, I don't think you need that much coding knowledge. I will say for the last challenge, I did have to write my own code to break the cipher, but if you know a basic language and you know how to code relatively comfortably in it, I code mine in Python. You can probably do all the challenges no problem if you have the coding knowledge, but you don't need that much.
So obviously you heard about the competition from your friends, but how would you recommend that someone like me maybe get involved in doing other competitions like these?
So I would definitely recommend checking out the resources I mentioned on the site, which is cipherchallenge.org. They have a load of great resources on there. There's also some other websites such as Bugcentrics and Code.fr. And of course, make sure to participate in the National Cipher Challenge next year. I believe it's running about the same time, September to December. So you can register for that on cipherchallenge.org as well. And I definitely recommend registering for it and participating in it.
Also, how did you do in the competition in the end?
So I got the Ada Lovelace prize, which is £1,000.
Wow.
So I'm pretty happy with that.
That's really impressive. I think we're gonna wrap it up now, but thank you, William, for coming and talking to me, and thank you everyone for listening. But we're gonna head on now, and I hope you enjoy the rest of the jam. Bye.
Thank you.
That was a great interview. Thank you, Charlie and William. The next National Cypher Challenge will be later on this year, and you can find out more details about the challenge at www.cypherchallenge.org. We'd like to thank Abby, Alan, Kevin, Charlie, William, and the ever wonderful Sam for appearing on screen today, as well as Vincent, Stephen, Claire, Jack, and Andrew for doing all of the work behind the scenes. Thanks again to Nitec for offering us their office space to use for all of our Jam Lives. If you signed up for this event through Eventbrite, I'll have already sent you an email with a short feedback form for today's activities. If you can, please take a few minutes to fill out this form, as it gives us loads of ideas for how we can improve the Raspberry Jam Live events. And if you loved today's event and you want to take part in our next Raspberry Jam Live, the next one is themed around game design, and it's available at nraspberryjam-april-2021.eventbrite.co.uk. So that's everything from me. Thank you for joining us today, and we hope we see you next time.